So at this point we want to revisit this idea of the differential equations, kind of bring our memories back to that, and also talk about this idea of solving differential equations with integration, which before we hadn't really done. Okay? So let's start out here first of all with this differential equation y prime equals 2x over y. Now, if I'm doing this, so the first thing that I'm going to do is I'm going to rewrite that y prime as a dy over dx. Because as you're doing these, the one thing that you need to do before you do any integration is to, what? What we talked about? Separate the variables, okay? Separate the variables. So I'm going to multiply both sides of this equation by the y. So I have a y dy, and I'm also going to multiply both sides of the equation by the differential dx. So I have a 2x dx. Okay? Once I have that accomplished, then I can take the integral of both sides, and I get the integral of y is y squared over 2. Okay? And the integral of 2x is going to be 2x squared over 2, so just x squared. And then I put in the plus c. Okay? Now, if we want to solve this for y, I would go ahead and multiply, okay, and then square root. All right? One thing as you go through these, especially if you're manipulating things that have that c in there, would be to distinguish between the different c's. Don't just use c through all of it. But what we would have here, if I multiply everything by 2, I have a y squared equals x squared plus 2 times c1, or you could just call that a different c, c2. Okay? And then we would square root both sides. So y would equal the square root of x squared plus that c2.
Where's the
Not be 2x squared.
Okay?
2?
So not
Oh yeah, 2x squared, sorry. 2x squared. Okay?
Could you also make that 2c1?
You can. You can.
Okay.
Sometimes it just complicates the algebra later on. So, because if you're getting an equation for y, what you care about is that final equation. So, not what the original plus c1 happened to equal. Okay? Now, here's something with growth and decay models, okay? In many applications, it says the rate of change of a variable y is proportional to the value of y. If y is a function of time, the proportion can be written as follows. So dy dt equals k times y. All right, so if I'm going to go ahead and figure out a general solution, I can again separate the t's from the y's, in which case I would have 1 over y dy equals k dt, and k is a constant, right? That's the constant of proportionality, because it's directly proportional. All right, so we do this, and then we take the integral of both sides, and you'll notice what we happen to end up with is ln of absolute value of y equals k times t. All right. Now, how do we, well, plus c, plus c. And then how would we solve this for y?
Make e base.
Okay, make e the base of both sides. So I have e to the ln of y, which is just y. And over here I have e to the kt plus c1. Okay? Well, here I have y equals e to the kt plus c1. I'm going to separate that actually and make that e to the c1 times e to the kt power. All right? Now, e to the c1 is just a constant, right? So I'm just going to call that a regular old c, and I have c times e to the kt. Okay? And that, folks, is where we get the exponential growth and decay model from. That model that we've used thousands of times at this point in school. That's where it comes from, okay? The rate of change is proportional to our value. Okay? Now, we've recognized some things about this. C is the initial value of y, which makes sense. If you plug in a 0 for t, e to the kt is e to the 0, so that's 1. So all you're left with is that constant. That's your initial value. K is the proportionality of your constant. Okay, if you remember PERT, P times e to the RT, your principal was your starting amount. The R was the rate of growth or rate of interest. Here's a more general form, okay, where K is your rate of growth and C is your starting amount. As we've seen in the past, when that rate is positive, we have exponential growth. When the rate is negative, we have exponential decay. All right, so here, just a connection to something that we've had in the past. Okay, and there's the whole development down there. Okay, even though we derived it ourselves. Okay. So, let's look at using this and developing this without necessarily, using our exponential growth model. Okay, we know that our growth model is y equals c e to the kt. All right, the rate of change of y is proportional to y. That means y prime equals kt. When t equals 0, y equals 2. When t equals 2, y equals 4. What's the value of y when t equals 3? Okay, so as we're thinking about this, notice what we have here is we don't know the rate of growth, but we do know it's proportional, so we know we can use this model. Okay? Now, when t is 0, y is 2. What does that tell us? What's that? The initial value is 2, so that means c equals 2. So now I have my function y equals 2 e to the kt. So now what can I do? Yeah, use this other point that they've given us to determine what? The k. All right, we need the rate of growth. So I know it equals 4 when t is 2. Okay? So I get 2 equals e to the 2k. I do the ln of both sides. ln of 2 equals 2k. And then I divide by 2. So k is a half ln of 2, which is also ln of radical 2. Okay? So my model here is y equals 2 e to the t times ln of radical 2. Okay? Now, can that be simplified? Yes. Okay. We don't have to necessarily, because it says what is the value of y when t is 3. I can plug in 3 here and figure that out. Okay, so y of 3 is simply 2 times e to the 3 times ln of radical 2 power. Okay? And what does that end up equaling?
I think it says it on the graph.
Oh, is it over here?
Yeah.
5.657? Okay. Now, by the way, you'll notice here, I told you we could simplify that y a little bit more, right? I could rewrite this y as y equals 2 e to the ln of radical 2 to the t power, right? What's e to the ln of radical 2? Radical 2. So this would be 2 radical 2 to the t power, or 2 times 2 to the t over 2 power. Okay? Now that obviously does not have a base of e. But what we just showed is that any of these situations where we do have a proportional rate of change, a rate of change that's proportional to y, we can write it as a growth or decay function with a base of e. Okay? The k, or the rate may not necessarily be as obvious or something like that, but it can be written that way. Yeah.
Is that 0.3466 just ln of rad 2? Or just
Yeah, I'm sure
instead of ln?
that's got to be ln of radical 2.
So they're just
Yeah.
doing that instead of ln.
Yeah. They just rounded it to the decimal. Okay? Now here's a decay model, a radioactive decay. Now guys, you guys are used to dealing with half-lives, right? And if you had the half-life formula, you know, the half-life formula says that the amount that you have left is your starting amount times 1/2 to the t over k power, right? So if I'm looking at isotope Pu plutonium-239, 24,100 years, okay, and I'm starting with 10 grams, then my amount after a certain number of years would be 10 times 1/2 to the t divided by 24,100. Okay? But again, that has a base of 1/2 in the exponential portion. We can actually use the model that we were just looking at to figure out an alternative form of this model. Okay? If we look at it as y equals c times e to the kt, we know the c is 10, that's our starting amount, 10 e to the kt. The thing here is we need another point to figure out what k would equal. What would another point equal or be?
Y prime equals.
T equals 24,100, and it's B, and it's 5.
Okay, the point, another point we would know on the model would be after 24,100 years, we would end up with 5 grams, right? Because that's 1 half-life, so half of 10 would be 5. Okay, so now we could use that in the model, y is 5. 10e to the k times 24,100. And then we divide. We have a half equals e to the 24,100 k. We do the ln of both sides. And then we'll end up dividing both sides by that 24,100. ln of 1/2 over 24,100. So the model we have in this case is y equals 10 e to the t times ln of 1/2 over 24,100 power.
So this is really just giving us a more generalized way of doing it.
It's a more generalized way. Half-life, we had that special formula. For compound interest, we had a special formula. Here's a more general formula that we can use that applies anytime the rate of change is proportional to the amount. Okay? So any kind of exponential growth or decay problem. Okay? What questions do you guys have? Yes?
For the actual problem to use plugging 1 to y.
We forgot to answer the question. Yeah. That's a question all of us still have. All right. How long does it take? So we're solving for a t when y is 1. So yes, we would then plug in 1. Okay, and I'll go ahead and divide by 10. E to the t times ln of 1/2 over 24,100. Okay. And notice one nice thing about this is when you're doing this, you don't have to mess with the change of base formula because your base is already E. Okay, so we now have ln of 1/10 equals t times ln of 1/2 over 24,100. And that means that I'm going to multiply by 24,100 over ln of 1/2. So I get t equals this. ln of 1/10 times 24,100 over ln of 1/2. Okay? Can someone help us with the calculator work? What time does that give us? Okay, is it a big number? First of all, let's think about this, okay? Let's think about this. I know it's going to take 24,100 to get down to 5. And another 24,100 years, it's going to get down to 2.5. And another 24,100 years, it's going to get down to 1 1/4. So we're at 72,300 years. So our answer should be big. What'd you get?
I got 80,058.467.
Does that make sense based on what we just talked about? Yeah. To get another 1/4 gram gone, it would take another about 8,000 years. So yeah, that makes sense. So 80,058 years, 0.467 years. That's a long time. So, anyways. Okay, now what questions do you guys have? Anything?
So, as to not remember like every individual formula, you said there's like a general one. Would that be like the e to the kt?
Yeah, this c e to the kt is for any kind of exponential growth or decay, no matter what the context you're dealing with. This same formula can be used. Okay, and you can develop that formula as long as you know any 2 points. The reality is, in both of these examples, we were told what the starting amount was, but we actually don't have to. If we know any 2 points, we could figure out what C was and what K is, because we'd have 2 different equations with 2 unknowns, once we plug in those 2 different points. Yeah.
If it was like not half-life and it was a different problem, or something like that, interest, compounding interest, what other point would you use besides the starting amount, like to get your formula?
Let's see here. You would have to know some other point. Like for example, if you were talking about an interest, let's say you didn't know what rate of interest you were making, you didn't know how much you started with, but you knew that after a year you had this much money in your account, and after 18 months you had this much money in the account. You could use those 2 with this model to figure out how much you started with and what the rate was that it was growing at. So.
That y prime equals kt is just saying that they're proportional, right? The c and the y.
Yeah, the y prime equals kt was the whole, that's really what the definition of an exponential growth or decay function is. It's something where your rate of change is changing as your amount changes. Okay, it's proportional, like you're increasing 6% of the each time. So, all right. So at this point, we're going to do some practice with these. Here are some where you're just solving differential equations. Make sure you separate variables first, okay? And then we have some others where you're given the fact that something, the rate of change is inversely proportional or is directly proportional. Make sure you pay attention to the language of how it's proportional, because that'll impact things here. Okay? So why don't you use the rest of this time, let's work together to try to work through some of these and figure them out, okay? All right.